Hey guys, good afternoon. I'm going to talk to you today about 3.2 and 3.3, which continues on from our two variable stats unit. So for the purpose of this activity, I will upload as well your blank copies of 3.2 and 3.3, just so that you can have blank copies in case you do have a printer at home, and again, you want to write in your lesson notes, and you can put them into your binders that you have. If you don't have a printer, no worries. I will also upload the final product so that you can just see and follow along through the video, and also reference the textbook pages that I have uploaded into Etsy. Okay, so just going back to what we talked about in 3.1. So in 3.1, it gave you a breakdown of scatter plot. So just remembering the strength, so the correlation coefficient. So it being somewhere between -1 to +1, and being able to determine how strong that is. So remember the strength of the line. If it's at -1, we call that a perfect strong correlation, whereas +1 would be a positive strong correlation. 0 would be no correlation at all. Okay, so what I have here is your linear regression. This is 3.2. I'm going to go over the 3.2 as a finished copy, just because there's lots of calculations, and I think this better suits how I would approach 3.2, and then in 3.3 we'll fill it in together with the video. So regression is a technique for determining the relationship between a dependent and an independent variable. Okay, so again, going back to the idea of we're looking at now two variable stats, so we want to see what their relationship may be, and we can do this while using an equation that will help build off of this information. Now, you might recall in grade 9 when you reviewed interpolation and extrapolation. Okay, so interpolation is when you look inside the data. Okay, so for instance, if you have a graph, and you wanted to find a point anywhere within the given line, you're looking at any data points that exist anywhere on that line itself. Okay, that would be interpolating because you're looking inside of what's given. Extrapolating or extrapolating would be anywhere outside. So for instance, if you wanted to know what this point would be, you can use an equation to help figure out what that point may actually be in terms of accuracy, or you can just extend that line and try to eyeball it as best as you can. So there's this method called the least squares method, and it has a line of best fit that you are considering here. Okay, and what's important about what today's lesson is about is this idea of a residual. So the vertical deviation between each data point from the line of best fit is called the residual. So it's actually using a method that we can calculate the difference between the y at the data point and at the point that lies on the line of best fit with that same coordinate. So again, if you're looking to extrapolate, this becomes very handy, but basically we're reviewing our knowledge of scatter plots, putting that with our y equals mx plus b format, because there is a formula that mimics it. It's just a little bit different because we're looking at residuals for this one. And we're basically analyzing that line. Okay, so that is our line. You'll notice for the line of best fit in the least square method, residuals that are positive for points that are above the line. So in this case, this would be positive because that square that I've just highlighted is above a line. And then anything that is negative, I'll highlight now in green, would be below the line. Oh, it's not the green. There we go. Okay. So our formal equation that we'll be looking at is as follows. So you'll see it will be y hat, because it has a little hat on top, a times x plus b. Now, you might think, well, what does a stand for? So for a, we need to do a side calculation. So a is going to be equal to n multiplied by the sum of x times y, subtracted by the sum of x times the sum of y, divided by n times the sum of x squared minus sum of x, and then squaring that value. Okay, so this finds a itself. If you want to find b, you'll see in this bubble here, b is equal to the sum of y minus a times x bar. Okay, so that's y bar minus a times x bar. Okay, and that helps to find what b is. Okay, so sorry, I think I said sum earlier. Just to clarify, b is equal to y bar minus a times x bar. Okay, so that's finding the average, if you recall, for x bar. That's like finding the mean for all your x value points, and we're also finding the mean for all our y value points. Okay, so how does this apply and how would you use it in a given situation? So we can scroll down. Our goal is to determine the equation of the line of best fit. Okay, so we are looking for y hat is equal to a times x plus b. So what would happen would be, you would take all of your x values. So here we're comparing income versus age. So we're seeing what type of relationship it does indeed have. You'll notice for your x independent axes or variable, you have 1, 2, 3, 4, 5, 6, 7, 8 values. And what you will do is you would find the sum of them. Okay, so when you sum up all those 8 values, you do get a sum of x, which is 292. Okay, you then can do the same thing with your dependent variable. So find the sum of y, so we're going to add up those same 8 values. Okay, and then to make life a little bit easier for you, you'll see for your x squared and for your x times y, this says the sum of all the values to this point is 9,427. So that means we did 33 squared plus 25 squared plus 19 squared plus 44 squared plus 50 squared plus 54 squared. That's just to make your life a little easier in terms of, you know, up to this point, this is what the value would be. I know you know how to square values, so that's just used to help get along with the lesson a little quicker. Okay, so obviously you're going to add 9427. You will add that with 1,444, which is 38 squared. You'll add that with 29 squared, which is 841, and the sum of x squared would then be 11,712. The same thing goes for x times y. Okay, so x times y, again, you're multiplying your age times income going horizontally across, and then you're going to take all of those values and you're going to find the sum of x times y, which is in this case 13,221. So this was done all in 3.1 in terms of how to work with the table. Now what we're going to do in addition to that is find x bar. Okay, so this is your mean of x. And then we're going to find y bar, which is your mean of y. So we will add up all our x values, divide by 8 because there are 8 values. Add up all our y's, divide by 8 because there are 8 values as well. So you'll notice x bar is equal to 36.5, y bar is equal to 41.125. So to find the equation of the line of best fit for our residuals, we need to do a little bit of calculations here. Okay, so we need to first find out what A is, and we need to find out what B is. Okay, we're going to leave y hat in there, and we will leave x in there, similar to y equals mx plus b, where we would leave y and we would leave x. So to find x, A, we would do the equation that I'm highlighting right here. Okay, and with that, you need to take all the values that we use in our chart above, so our sum of x or sum of y or sum of x squared, sum of xy, and we're going to apply that to isolate for A. Okay, so you'll see everything on the right side just needs to be worked out using the values in the chart above. Once you do that successfully, you will have a finished value of A is equal to 1.15. Okay, so we got this value here. 1.15. Now, to find our B value, we're going to use the equation of y bar minus A times x bar. Okay, so that's where the bottom part of that table becomes very useful, where we found x bar, we found y bar, and we actually have A because we just worked on it in the previous step. So once you work that out, we get y y bar minus a times x bar. So once it works out, you get b is equal to negative 0.85. Okay, try it on your own as well. So play around with your calculator to make sure that you actually get these values, just because we're number crunching so much. So you got to make sure that you're able to input into a calculator and know how it works out for you. Okay, so together, if b is now equal to negative 0.85, the equation of this line that we have will be y hat is equal to 1.15x minus 0.85. Okay, so where this becomes handy, right? So again, if we look back at our variables, so we have age and income, x and y. If we wanted to figure out the income for a 42-year-old, we can actually do this as an estimate by replacing x, which represented age, with 42, like you've done in the past. We've done this work just, in different settings. And you would sub in 42 for x, and you would isolate for y, and in this case, y would be 47,450, okay, because it is in thousands. Okay. Now, if you look in your textbook, that becomes very handy in having the textbook, because this is a similar example to what was used in your 3.2 section. All right, so moving along, example 2 is to determine the equation of the line of best fit and the correlation coefficient. So again, equation of the line of best fit is the focus of today's lesson, which is on 3.2. Calculating the correlation coefficient is what we did last day in 3.1. Okay, so once again, you see that we have our x variable of midterm, y variable of final. We have our x squared or y squared and our x times y. Like we mentioned above, everything is already calculated for you. This is, again, just the finished copy, but I strongly urge you to fill in your own notes. That will be the focus of today's lesson. So just trying to understand and comprehend, how to create this line of best fit. You'll see as I scroll down here, I calculated the correlation coefficient first. So we're at 0.56. So it's definitely in the positive range, and we're at a moderate value because it's at 0.56. So I would say this is positive, moderate correlation. Right, so it's a positive value. 0.56 is about halfway between 0 and 1, and it has that type of correlation. Okay, similar to how we did in example 1, where you isolate for A, we figure out what A was. A was equal to 0.78, and then doing the same thing with B, 11.83. Okay, so together, if we were to finalize that equation, it'd be y hat is equal to 0.78x plus 11.83. Okay, so again, it is very similar to y equals mx plus b, right? It has that same setup. Where it's different is because we're looking at the residual, right? We're not looking at rise over run. When you did rise over run in grade 9, you're assuming that you had a constant rate of change. We're assuming that if we had a slope of 1 over 3, that meant for every rise of 1, we would run 3, and it would continue in that stair pattern. That's not the case in a scatter plot, as you know. Right? So in a scatter plot, you're trying to convey and determine what type of relationship it actually may have based off of finding the correlation coefficient, and also trying to figure out what that equation of the line may be. Okay? Great. So that wraps up 3.2. Okay? I'm just going to scroll down a little bit, and I will walk through 3.3 with you. All right. Okay, so for 3.3, this is on residuals and the coefficient of determination. Okay, so as the first 3 points it reads from yesterday, which is the 3.2 lesson, the residual is the difference between the values of y and the value of y hat with the same coordinate of x value. Okay, so again, looking at that difference, this is what y is. This is what the predicted y value would be if you follow through with that equation. Now, a lot of predictions are often made, again, if we go back, I don't know, in class I would use that example of the population in Ajax, right? If we were to predict what the population of Ajax would be by 2040, we can use something like the equation we created above and predict what that value should be based off of the trend. Right? Those are all good things that happen when you look at two variable sets and you're able to create that relationship. Now for today, we're going to talk about a residual plot and actually graph this. Okay, so residual plot displays the arrangement of the residuals around the line of best fit, and it actually can determine how far away you are from the line that's given to you. Okay, so for residuals, your equation is going to be calculated by E is equal to y minus y hat. Okay, so we're going to create a residual plot from yesterday's data, so from 3.2's data, and we are going to use this equation. Okay, so with that, I want you to think of this. When we have a value of x as 77, okay, how we're going to actually calculate our E value is looking at our y's. Okay, so we have y and y hat. So I'm just going to highlight that out for you. So if you wanted to find the expected value, you can actually interpret what you have here. So if we take 82 in the y and subtract it from 71.898, we get that expected value of 10.102. Okay, you can do that in your calculator. So if you follow through with that, you can do some algebraic steps to help figure out some missing values. Okay, so if you wanted to find out, in this case, I'll use a different color. So y hat, that would be just interpreting this formula that we have here. You'll notice we don't have what y hat is. So what we're going to do is we're going to sub in $71 in for x, and that will find out what our y hat is. So we're going to use the equation there, 0.777 instead of x. We'll replace that with 71, okay, plus 12.069. Okay, so once you sub that in, we actually are using our line of best fit line, and we get a value of 67.239 once you work it out. Okay, now like I showed you earlier, if we wanted to find out what E is, E is equal to y, so I'll use a different color here. So in this case, 78 subtracted by our y hat value that we just calculated. So 78 subtract 67.239, and you should end up with a final value of 10.761. Okay, so we are using two formulas here. Just because we have some unknowns, we are using it for our residual, which is calculating E, and we're also using it when we're trying to find out what y hat is, which is our line of best fit equation. Okay, so I actually have these already completed. So what I'll do is I'll just write them in. And I do strongly urge you guys to try this on your own, just to ensure that you are doing well with calculating and manipulating these equations. Oops, 0.017. $85.114, 86.668. I'm rounding to 3 decimal places because, as you know, the more decimals that you include, the more accurate your answer is. So for the purpose of today's lesson, I would round to about 3 decimal places. Three, 2. Okay? So we're going to actually create a residual plot on the grid space that we have here below. Okay, so this is what we're going to look at. We're actually going to compare E versus X, or X versus E. Okay, so the value of X, which is the real value in the independent axes, okay, compared to your expected value, which is going to be a residual. And why this is helpful is because it basically will show all the outliers that apply. Okay, so I apologize. There's no ruler function on here, so I will just have to freehand it. Okay, so we're going to measure this by E. And 1, 2, 3, 4. There we go. X. Okay, so I'm going to go up by 5, so that could be 5. That could be 10. And then we'll do negative 10. Negative 20. Negative 30. Okay, so every 2 boxes I'm doing 10 units, or every 1 box is 100 units in the y-axis. Okay, in the x-axis I have quite a bit of room, right, because my x value, the highest value is 99. So let's see here, we could do a little, first value there, we could do 10, 20, 30, 40, 10, 20, 30, 40, 50. You know what? We'll do a little break just to make it a little easier on us. Okay, so this can be 50. We'll do 52, 54, 56, 58, 60, 72, 4, 6, 8, 80, 2, 4, 6, 8, 90. I'm not going to have enough room. Let's do one more time. So we'll do 50, 60, there's that line, 70, 80, 2, 4, 6, 8, 90, 2, 4, 6, 8. Okay, 99 will just be outside of that, but you know what, that's the best we could do, so no worries. Okay. Okay. Now, once you plot this graph, I can actually show you what your finished copy would be, just to make it a little quicker. Okay, so you can see here that my line, let me make that down a bit. Okay, so all the points that I drew are in blue, and we can see those values that are at the very bottom are actually our outliers, right? Because they are so far from the data trend, which is drawn in the red line, right? If we were to think about where most of our points lie, Most points are above that line, mostly in the same vicinity. But those two lower points, so at around, I guess it would be around 72-ish and 80, 81 for that value, that's very, very far away from where the rest of the data is. Okay, so that would be a residual plot where you would compare E, your expected value, compared by X, which is your data point value that's given to you. Okay. Now, for the correlation of determination, so looking at R squared, recall that Pearson's correlation coefficient R is a measure of linearity of the data, so how to produce a line, and so it can only indicate how closely a straight line fits the data. Now there's something called the coefficient of determination, R squared, and it's defined such that it applies to any type of regression model and has values from 0 to 1. Okay. For any type of regression, the model of best fit will be the one that has the highest value of R squared. Okay, so again, if we look at our regression line, okay, and we want to figure out an observed data point. So you can see there in purple, you have your observed data point. Now, based off of that dotted line, which is looking at Y bar, we can actually determine and see how our values do fall close to that predicted value point. Okay, so when we actually calculate R2, it can be calculated by comparing either the explained or unexplained variation in the response variable Y to the total variation in the response variable. So for R squared, which is your coefficient of determination, it will be equal to this. 1 minus, excuse me, the sum of y minus y hat squared over the sum of Okay, sorry about that. I just had a little cough. So just going back to R2, so I've written out your equations that you can use. Okay, so R2 can be 1 minus sum of y minus y hat squared divided by sum of y minus y bar squared. That's the unexplained, okay, and I'll talk a little bit about what explained versus unexplained versus explained means, and we'll see it actually when we go through the data set. Another equation for R squared, you can also use the sum of y hat minus y bar squared divided by the sum of y minus y bar squared. Okay, so basically for your coefficient of determination, which is our R squared, you're looking at observed data points, and we're trying to determine what that value could be based off of the residual squared. Okay, so if we just take a look at this point that's highlighted here, a value of R squared, if we get that when we work it out, is equal to 0.7. It can be interpreted as approximately 70% of the variation in the response, so looking at your dependent variable, can be explained by the explanatory, the independent variable. So in English, this means that R2 statistic gives some information about the goodness of fit of a model to the data. So how well the model approximates the data. Now, it doesn't mean that a higher correlation means that that's causation, right? So again, it still can be determined by what the variables actually are. Okay, as I've always said from the beginning, data management or statistics is looking at how we can interpret values and what they may mean. Okay, and R2 basically just explains how two variables are related within the set of data that has been provided. Okay, so we're interpreting, we're trying to make an understanding of the two variables that are given to us. Okay, so how this can apply in a chart form. Okay, so we have our sum of y squared, y bar, and our line of best fit equation. Okay, so notice there are a couple of new equations here. Okay, that's just going to be y bar, that's y bar. Okay, good. So with the data that's given to us, we can find the difference between y and y bar, and then squaring that value. And I've done the first couple for you. The next couple that we have would be 730.23, 26.12, and then we would have a total of 3,872.89. Okay. Similar to our last two columns, y hat minus y bar. So taking a look at this column, taking a look at y hat, and then squaring those values. So please try it on your calculator for yourself so you can see how these numbers interact. Okay, now I'll show you, we can use both equations for our correlation of determination with our unexplained oops. Sorry for the tickle. Okay, and for our explained. Again, applies to any type of regression model that can have values from 0 to 1. And we are basically determining the type of regression and basically just comparing values that can be explained, which can be at random, or from our model, and basically looking at how they vary. Okay, so ultimately, if you want to figure out the proportion to see if your model actually explains a good expected value, you can use any of those two formulas, with the unexplained and explained, and you'll notice that they do end at the same result. Okay, so that takes care of 3233. If you have any questions, feel free to ask. You can practice those questions that are in your booklet, and please try out the lesson notes for this class so that you can actually work through the examples together with the video. Okay, take care.
Also, guys, please just read this last little section on be careful what you read. It just gives you some insight onto what the correlation of determination connect.